Welcome to chapter 4 of number theory. This is one of the important chapter in this number theory. In this chapter we are going to utilize all the concepts till now we developed. In this chapter we are going to prove an important theorem called quadratic reciprocity law. But before going to prove the quadratic reciprocity law, we are going to prove some intermediate results like Euler's criteria, then Gauss lemma, etc. And in this module we are going to define and prove various properties of primitive roots modulo n. First we are going to show the existence of primitive roots modulo n. That means for a given n, the primitive root modulo n need not exist. So we are going to show that primitive roots of a given n exist only if n is of the form n is equal to 2 or 4 or p power k or 2 into p power k, where p is an odd prime. So we are going to see primitive roots of modulo n for a given n now. In chapter 4 we are going to see primitive roots and quadratic residues. In the module 1 we are going to discuss about primitive roots. The learning objectives of this module are group of units of Zn and order of an integer modulo n where n belongs to n, and the primitive roots of n. Group of units of Zn, let n belongs to n natural numbers, then we define un is equal to x belongs to n such that 1 less than or equal to x is less than or equal to n, where x comma n equal to 1, that is GCD 1. So un is set of all numbers which are relatively prime to n and less than or equal to n. So the un is set of all numbers 1 to n relatively prime to n. For example, u8 is equal to 1 comma 3 comma 5 comma 7. It is because these 1 3 5 7 are relatively prime to 8. u12 is equal to 1 5 7 and 11. So in general up equal to, where p is a prime number, then up is equal to 1 2 3 up to p minus 1. So why we are interested in these numbers? We know that Zn minus 0 does not form a group with respect to multiplication. As for example, if I take Z6 is 0 1 2 3 4 up to 5 is a group with respect to addition modulo 6. But Z6 star, that is if I remove 0 from it, then we have 1 2 3 4 5 is not a group with respect to multiplication modulo 6, as 2 into 3 equal to 6, 0 mod 6, and that does not belongs to Z6 minus 0. Also the elements 2 3 4 do not have multiplicative inverses modulo 6, or equivalently Ax is congruent to 1 mod 6 does not have solution whenever A is equal to 2 or 3 or 4. So that is why we are looking for un. So un is a group with respect to multiplication modulo n. So the answer is yes, that is un is a group with respect to multiplication. So but one can verify easily. The next question is un, that is a set of all integers less than n which are relatively prime to n, is going to be a cyclic group or not. So this is now we need to explore. The answer is no. For example, un is not cyclic. In general, un is cyclic only when n is equal to 2 or 4 or p power k or 2 into p power k, where k is greater than or equal to 1, where p is an odd prime. For n is equal to 2, 4, p power k or 2 into p power k, k greater than or equal to 1, the generators of un are called primitive roots of modulo n. So in this module our topic is primitive roots modulo n. So primitive roots modulo n are nothing but the generators of this group un. un is a group with respect to multiplication and its generators are primitive roots of modulo n. For example, n is equal to 5, u5 is equal to 1 2 3 4, 2 comma 3 are primitive roots modulo 5, as 2 power 0 is 1, 2 power 1 is 2 modulo 5, 2 square is equal to 4 modulo 5, 2 cube is equal to 3 modulo 5. So we are getting all the elements in u5. So 2 is one of the generator. So 2 is a primitive root modulo 5. Similarly, we can verify that 3 is a primitive root modulo 5. So that means 2 and 3 are generators of this cyclic group u5. Further, Un is set of all generators of the additive group cyclic group Zn also. So, this is an interesting exercise to do. Un is set of all generators under additive cyclic group Zn. Zn is a cyclic group with respect to addition. So, Un is collection of all elements in Zn that have multiplicative inverses, hence Un is called group of units of Zn. For a fixed positive integer n, Euler's theorem says that for any a belongs to n, GCD of a comma n equal to 1, then one has a power phi of n is congruent to 1 mod n. Therefore, so there exists a positive integer say x such that a power x is congruent to 1 mod n. So, and a power k is not equal to 1 mod n. So, obviously from Euler's theorem that x is less than or equal to phi of n. So, that is prompted this definition. Fix a positive integer n and a belongs to n with GCD of a comma n equal to 1, then the least positive integer x such that a power x is congruent to 1 mod n is called order of a modulo n, denoted order of a n. So, if order of a n is equal to phi of n, then a is called primitive root modulo n. This is another way to define primitive root modulo n. So, for example, n is equal to 13, 3 power 1 is 3 congruent to 3 mod 13, 3 square is 9 congruent to 9 mod 13, 3 cube is congruent to 1 mod 13. That means 3 power 3 itself we got 1. So, order of 3 modulo 13 is 3, whereas 12 square is congruent to 1 mod 13. So, order of 12 modulo 13 is 2. In fact, n minus 1 is congruent to minus 1 mod n for any n. So, order of n minus 1 is equal to 2 only. So, whereas order of 2 modulo 13 is equal to 12, that is equal to phi of 13. So, 2 is a primitive root modulo 13. So, example of non-existence of primitive roots will show that there are no primitive roots modulo 16. So, U16 as we know that it is 1, 3, 5, 7, 9, 11, 13 and 15. So, phi of 16 is equal to cardinality of units of 16 U16, that is equal to 8. One can verify easily that a power 4 itself is congruent to 1 mod 16 for all a belongs to U16. That means that order of a is at most 4. So, there is no element whose order is equal to 8. So, there are no primitive roots modulo 16. So, another example, fix a positive integer n and a belongs to n with GCD of a comma n equal to 1. If a is a primitive root of n and un is equal to a1, a2 and so on a phi of n, then we have that a1, a2 and so on a phi n is equal to a square and so on a power phi of n modulo n. So, this result holds only when if a is a primitive root, then all elements in un can be expressed as a. This is the what prompted earlier to define that the generator of un is the primitive root. So, a is a generator now. So, if a is a primitive root modulo n, then a power I modulo n and a power j modulo n are distinct for whenever one is less than or equal to I, not equal to j, less than or equal to phi of n minus 1. Moreover, GCD of a comma n equal to 1 implies that GCD of a power k comma n is also 1 for all 1 less than or equal to k less than or equal to phi of n. Thus, we got the required result. Number of primitive roots. Now, once we saw the existence of primitive roots will not exist for all n, but once it exists, then how many are there? So, this example answers that one. Fix a positive integer n and assume that n has a primitive root, then the number of primitive roots of n is equal to exactly phi of n. So, note that if a is a primitive root modulo n, then order of a n is phi of n. Now, observe that 1 less than or equal to k less than phi n, order of n, order of a power k modulo n is also equal to phi of n if and only if GCD of a comma phi of n is equal to 1. This is similar to the primitive nth roots of unity which we proved in the previous module. By definition, the number of integers which are relatively prime to n and relatively prime to phi of n is equal to phi of n, hence we got the required result. So, now we will see an example to find all primitive roots of modulo 13. Using an example given before, we see that 2 is a primitive root modulo 13. As phi of 13 is equal to 12, the numbers 1, 5, 7 and 11 are co-prime to 12. We see that 2 power 2 equal to 2 power 1 and 6 equal to 2 power 5 modulo 13, 11 equal to 2 power 7 modulo 13, 7 equal to 2 power 11, they are all primitive roots modulo 13. So, the primitive roots modulo 13 are 2, 6, 11 and 7. Thus, there are 4 primitive roots. Now, we are going to show that if n is equal to 2 power k for some positive integer k, then n has a primitive root modulo n, that is un is cyclic whenever k equal to 1 or k equal to 2 only. That means, if I take n equal to 2 power 3 or 2 power 4 and so on, then then un is not cyclic or there is no primitive roots modulo n. For example, if k equal to 1 or k equal to 2, then it is easy to see. If k equal to 1, then n equal to 2 just. So, u2 equal to only 1, that is clearly cyclic and generated by 1 itself. When k equal to 2, then n equal to 4, then u4 has equal to only 1 comma 3. A group of order 2 is always cyclic, so it is indeed cyclic. So, we proved that when k equal to 1 or 2, un is cyclic or n has a primitive root modulo n. So, we now show that 2 power k is not cyclic whenever k is greater than or equal to 3. To do so, it is sufficient to prove that order of x modulo 2 power k is less than phi of 2 power k, which is equal to 2 power k minus 1 for all x belongs to u 2 power k. In fact, we will use induction to show that x power 2 power k minus 2 itself is equal to 1 modulo 2 power k for all x belongs to u 2 k whenever k is greater than or equal to 3. So, base case when k is equal to 3, you take u8, that is 1 3 5 7. It is easy to see that 3 square equal to 9, that is congruent to 1 mod 8, 5 square is 25, that is congruent to 1 mod 8, 7 square is 49, that is also congruent to 1 mod 8, and order of A is for every element in u8 is less than or equal to 2. So, u8 is not cyclic, hence there is no primitive root modulo 8. So, we proved the base case. Now, induction hypothesis, suppose the result is true for k, where k is greater than or equal to 3, that is we will assume that x power 2 power k minus 2 is congruent to 1 mod 2 power k for all x belongs to u 2 power k with k is greater than or equal to 3, or equivalently x power 2 power k minus 2 is equal to 1 plus m into 2 power k for some positive integer m. We will now prove that the result is true for k plus 1. That is, we need to show that for every y belongs to u 2 power k plus 1, y power 2 power k minus 1 is congruent to 1 modulo 2 power k plus 1. So, let us take y belongs to u 2 power k plus 1, then either 1 is less than or equal to y is less than 2 power k, or y is equal to x plus 2 power k with 1 less than or equal to x is less than 2 power k. Case, so in either case, that is y is equal to x plus t into 2 power k, where t belongs to 0 or 1, and 1 is less than or equal to x is less than 2 power k. Hence, using k greater than or equal to 0 and binomial theorem, y power 2 power k minus 1 is equal to x plus t into 2 power k whole power 2 power k minus 1, which is equal to x power 2 power k minus 1 modulo 2 power k plus 1, which is equal to x power 2 power k minus 2 whole square modulo 2 power k plus 1. So, thus by using x power 2 power k minus 2 is equal to 1 plus m into 2 power k, for some positive integer m and k greater than or equal to 3, we will get that y into y power 2 power k minus 1 is congruent to x power 2 power k minus 2 whole square modulo 2 power k plus 1, which is equal to 1 plus m into 2 power k whole square, which is equal to 1 plus m into 2 power k plus 1 plus m square into 2 power 2 k, which is congruent to 1 mod 2 power k plus 1. So, with that we proved that u 2 power k is cyclic only when k equal to 1 or k equal to 2. We proved that if n is equal to 2 power k, then un is cyclic when k equal to 1 or k equal to 2 only. Now, we are going to prove that un is cyclic whenever n is a prime, and we will also give the sketch of the proof for un is cyclic whenever n is a prime power. Now, we will show that u p power k is cyclic for all odd primes p and for all k greater than or equal to 1. To do so, we need the following results. So, division algorithm, as we proved division algorithm for integers, now we are going to prove division algorithm for polynomials. The proof is almost similar. Let f(x) is equal to a n x power n plus a n minus 1 x power n minus 1 and so on plus a 1 x plus a 0 be a polynomial of degree n greater than or equal to 1 with integer coefficients. If g of x equal to x power m in plus b m minus 1 x power m minus 1 and so on plus b 1 x plus b 0 is a non-zero polynomial, then there exist a unique polynomials q of x and r of x with integer coefficients such that f of x equal to g of x into q of x plus r of x, where either r of x is identically 0 polynomial or degree of r of x is less than degree of g of x, which is equal to m. Okay, this is called division algorithm for the polynomials. So, we going to use this result now. So, we will give the proof. First, we will prove the existence of the polynomials q of x and r of x. The result is clearly true if degree of f of x is less than degree of g of x, as in this case f of x can be written as 0 into g of x plus f of x itself. So, let us assume the result for polynomials of degree less than n minus 1 and consider the polynomial f of x is of degree n, and if n is less than m, we are done. So, we will assume that n is greater than or equal to m. So, then we will see that the polynomial h of x is equal to f of x minus a n into x power n minus 1 into g of x has integer coefficients and degree of h of x is less than or equal to n minus 1. Thus, by induction hypothesis, there exist polynomials q1 of x and r1 of x with integer coefficients such that f of x minus a n into x power n minus 1 g of x, that is equal to h of x, which is equal to g of x into q1 of x plus r1 of x, with either r1 of x is 0 polynomial or degree of r1 of x is less than degree of g of x. Hence, f of x equal to, now if you bring the remaining term to that side, then g of x into a n into x power n minus 1 plus q1 of x plus r1 of x. Thus, we obtained a required result as we obtained q of x as a n into x power n minus m plus q1 of x and r of x as r1 of x itself. So, the proof of uniqueness is left to the reader. So, he can prove, now take two representations and prove that they are equal. The proof is goes similar to the proof which we done for division algorithm for integers. Now, the remainder theorem, this is a familiar result, those who are know the proof they can skip. Let f of x be a polynomial of degree n greater than or equal to 1 with integer coefficients, then f of a is a remainder when f of x is divided by x minus a. The division algorithm applied to polynomials f of x and x minus a gives us the unique polynomials q of x and r of x such that f of x equal to x minus a into q of x plus r of x. That means we are applying division algorithm for f of x and x minus a as a g of x. Then r of x is either 0 polynomial or degree of r of x is less than degree of x minus a, which is equal to 1. Hence, in either case r of x is a constant. Moreover, f of a is equal to a minus a into q of a plus r of a, so which is equal to r of a itself. So, r of x is a constant implies r of x equal to r of a, which is equal to f of a for all a. Hence, f of a is a remainder whenever f of x is divisible by x minus a. Another theorem is called factor theorem. If f of x be a polynomial of degree n greater than or equal to 1 with integer coefficients, then a is a root of f of x if and only if x minus a is a factor of f of x. Okay. So, x minus a is root if and only if x minus a is a factor of f of x. So, by division algorithm there exists q of x r of x such that f of x equal to x minus a into q of x plus r of x. That means we are applying division algorithm for f and x minus a, where r of x is a 0 polynomial or degree of r of x is less than degree of x minus a, which is equal to 1. If a is root of f of x, then f of a equal to 0. Hence, by previous lemma f of x equal to x minus a into r of x, as r of a equal to f of a, that is equal to 0. Conversely, if x minus a is a factor of f of x, then r minus x is a 0 polynomial, hence f of a equal to 0, thus we got the required result. So, now we are going to give an important result without which it is difficult to show that UP is cyclic whenever UN is cyclic whenever n is prime or n is prime power k. This is called Lagrange's theorem. What it says is, if f of x is a polynomial with integer coefficient, that is f of x equal to n into x power n plus a n minus 1 x power n minus 1 and so on plus a1 x plus a0 be a polynomial of degree n greater than or equal to 1 with integer coefficients. Let p be a prime number such that p does not divide a n, then f of x has at most n incongruent roots counted with multiplicity modulo p. So, we are looking in a modulo p. So, we will prove the result by induction on n, the degree of the polynomial. For n equal to 1, f of x equal to a1 x plus a0 with p does not divide a1. So, by using one of the previous theorem, we know that the linear congruence a1 x plus a naught equal to 0 mod p has exactly one solution modulo p. Suppose the theorem is true for all polynomials of degree less than or equal to n minus 1, and let f of x be a polynomial of degree n. If f of x has no root modulo p, then we are done. So, let us assume that alpha naught is an incongruent root of f of x of multiplicity k modulo p. Then using previous corollary repeatedly, we can see that f of x equal to x minus alpha naught power k into g of x modulo p for some polynomial g of x. Since leading quotient of g of x and f of x are same and degree of g of x is less than or equal to n minus 1. So, by induction hypothesis g of x has at most degree of g of x n minus k roots counted with multiplicity, so modulo p. So, moreover, g of alpha naught is not equal to 0, as alpha naught is a root of f of x of multiplicity k modulo p, and beta is a root of g of x modulo p if and only if beta is a root of f of x modulo p, as beta is not equal to alpha naught and f of beta equal to beta minus alpha naught power k into g of beta. Thus, f of x has at most n, which is equal to k plus n minus k incongruent roots counted with multiplicity modulo p. So, with that we proved the Lagrange's result. Now, we will see another theorem, that if p is a prime number, if d divides p minus 1, then x power d minus 1 has exactly d incongruent solutions modulo p. This result is also used to show that existence of primitive roots modulo p where p is an odd prime. So, since d divides p minus 1, there exists t belongs to z such that p minus 1 is equal to d into t. Hence, x power p minus 1 is equal to x power t d minus 1, which is equal to x power d minus 1 into x power d into t minus 1 plus x power d into t minus 2 plus and so on plus x plus 1. Let f of x equal to x power d into t minus 1 plus x into d power d into t minus 2 and so on plus x plus 1, then f of x is a polynomial with integer coefficients of degree d into t minus d, which is equal to p minus 1 minus d. Moreover, p does not divide its leading coefficient, hence by Lagrange's theorem, that what we proved earlier, f of x has at most p minus 1 minus d incongruent roots modulo p. But from our little theorem, we know that x power p minus 1 has exactly p minus 1 incongruent solutions modulo p. The roots are 1, 2, 3 and so on p minus 1. Hence, x power d minus 1 and f of x has exactly respectively d and p minus 1 minus d incongruent roots modulo p. Thus, we have the required result. Now, we are going to prove the required main result, that UP is cyclic whenever P is prime. So, theorem statement is, let P be an odd prime, then we have to show that UP is cyclic. In fact, we will claim that for each divisor D divides P minus 1, there are exactly phi of D elements in UP of order D. This gives us required result for D equal to P minus 1. We will have phi of P minus 1 elements in UP of order P minus 1. To prove the claim, we will consider the set gamma of D is equal to x belongs to UP such that order of x modulo P is equal to D. Now, we will prove that the cardinality of gamma of D is exactly equal to phi of D. Note that gamma of D is partition of the set UP, hence P minus 1 is equal to summation D divides P minus 1 small gamma of D. Also, by previous theorem, P minus 1 is equal to summation D divides P minus 1 phi of D. Thus, we have D divides P minus 1 phi of D minus gamma of D is equal to 0. Hence, it is sufficient to show that phi of D minus small gamma of D is greater than or equal to 0 for all D divides P minus 1. Note that the result is trivially true whenever gamma of D is empty set. Hence, let us assume that gamma of D is not an empty set. Let A belongs to gamma of D, then we have 1 A square and so on A power D minus 1. They are all distinct and incongruent solutions of the polynomial x power D minus 1. But x D minus 1 has exactly D incongruent solutions. Hence, gamma of D is subset of 1 A square and so on A power D minus 1. Now, let C belongs to gamma of D, then C equal to A power I for some I 1 less than or equal to I less than or equal to D minus 1. We claim that GCD of I comma D equal to 1. For if GCD of I comma D equal to J greater than 1, then C power D by J, which is equal to A power AID by J, which is equal to 1. Hence, order of C modulo P is less than D, a contradiction. So, order of C modulo P is equal to D. Thus, we have gamma of D is subset of A power K, where K comma D GCD equal to 1, where 1 is less than or equal to K is less than or equal to D. So, now we will give the proof for U P power K is a cyclic group. We will not give complete proof, we will just give the sketch of the proof. For the following result, we will prove the sketch of the complete proof is left to an exercise. Theorem, it says that P is an odd prime, then U P power k is a cyclic group for all k greater than or equal to 1. That means that after this theorem we can have that the primitive roots exist for n equal to p power k also. Since UP is cyclic, there exists a generator for UP. Let A be one such generator. Then we will show that either A or A plus P is a generator for UP square. So, you just try for this one. Take A is a generator for UP, then you have to show that A or A plus P is a generator for UP square. Finally, we show that if B is a generator for B square, then B is also generator for UP power k for all k greater than or equal to 2. As we notice, Lagrange's theorem is very useful in establishing the existence of primitive roots modulo n, and we are going to give further applications of primitive roots modulo n in subsequent modules. With this, we will end this module.